Section 9.2 today on parametric equations. Parametric equations are a way that we can get some really interesting graphs and be able to model things that we just can't do with the graphs that we're used to looking at. Okay, so let's pop over to Desmos and I'll show you a few of them. All right, so I just want to show you a few things that you can graph with parametric equations. So we've got this kind of weird sweepy looking graph. I'm going to show you how it graphs this in a little bit. So this could be, the flight of a bird going through the air, something else that we want to study, and clearly something that we would not be able to graph given our usual tools of y equals a function of x. And even our conic sections couldn't accomplish this, right? So got all kinds of interesting things that you can graph with parametric equations. All right, that one's really cool. And then you can even get kind of this complicated butterfly looking thing. All right, so I'm just going to show you how this is accomplished with equations in Desmos. I'll show you this first one. This was the little sweepy bird graph. Okay, so what's going on here is that instead of plotting y is equal to a function of x or an equation with just x's and y's in it, there's this mysterious t variable that's working behind the scenes. So in Desmos, we plotted this as an ordered pair where the x coordinate has its own formula in terms of t, and the y coordinate has its own formula in terms of t. And then we tell Desmos to let t range between -10 and +10. Okay, so that variable t is this behind the scenes variable that doesn't show up in the graph. It's just sort of pulling the strings and telling x and y what to do. All right, and these parametric equations get more and more complicated the prettier the picture is. All right, so like our little pointed star graph there had some sines and cosines cubed. Let's see, this one was the 5-pointed star. That's also got some sines and cosines in here. The equations are starting to go off of the little window there. This one's kind of cool. I've got this Desmos linked on our Moodle page, so you can play around with this one if you want to. You can slide this variable a around and b around to get different versions of this graph. And then the butterfly one, this one goes on forever. It's really big. Okay, so that's the x coordinate ends right there, and there's the y coordinate coming. Okay, you got cosines and e to the x's and sines and all kinds of stuff going on in there. And just by way of interesting point, when I was playing around with this, trying to figure out the upper bound for t, that 14.5, I accidentally crashed Desmos by putting a very large number in there. So I'm not going to do that here, but if you want to pull up the file and start putting in some bigger values for that upper end of t, this graph does some interesting things. All right, so let's go back to our whiteboard and talk about parametric equations. All right, so the equations that you're used to dealing with are what we call rectangular equations. Okay, so these are things like y equals x squared, and even our conic sections like x squared plus y squared equals 1. All of those equations that have the relationship between x and y sort of explicitly out there in the equation, those are called rectangular equations. All right, with parametric equations, like I said, there's this actor behind the scenes. And usually we call it the letter t. All right, and that letter t is called our parameter. Okay, and it's the variable that you don't see in the graph, but the one that's behind the scenes, pulling the strings and telling x and y what to do. Okay, so t goes over and acts in a formula that gives you the x coordinate, and then it also goes over and acts in a different function that gives you the y coordinate, and then you take those two numbers together to get your point, x comma y. So you don't ever plot anything involving t, just x and y. T is just telling x and y what to do. Okay, so let's just do an example of this. I'll give us a parametric equation to graph, and we'll do it kind of old school by plotting points. So we're going to graph x equals t squared minus 3, y equals t plus 2 for t between -2 and +3. All right, so like I said, we're going to plot points. So instead of making an x and y chart, we're going to make a t x and y chart. So t x, and I'll write the formula here so I can remember it a little easier, and y. All right, and they give us the values of t that they want us to use, which sometimes they do and sometimes they don't. All right, so I'm just going to hit all the integer spots for t between -2 and +3. Okay, so now all I'm going to do is just the plug and chug. I'm going to take those values of t and plug them into the equations for x and the equations for y. Okay, so I've plugged in the values t equals -2 through +3 into both equations for x and y. And again, when we go to graph, we don't pay any attention to what the t value is. We're just going to look at the x and y. So this table gives us a list of ordered pairs to plot. So I'm going to take the x coordinate of 1, y coordinate of 0. My x coordinate was 2, y coordinate 1. All right, so now I'm just going to go make an xy plane and graph my points. All right, so there are my 6 points that I've plotted. And if you kind of turn your head to the side, you can see that kind of has a parabola shape to it. So I'm going to go ahead and fill that in. All right, and notice that I stop at the points on the end, the 1 comma 0 and the 6 comma 5. I stop there because the problem asks us to graph it just for t between -2 and 3 inclusive. So I'm going to stop there and not put arrows on the end of the graph. Okay, and the last thing that I'm going to do is draw some arrows on this graph. Okay, so this is going to indicate that we started at this point here and that we ended at this point here. Okay, so putting the arrows kind of indicate where that is because you can't see the t in the same way that you can see in rectangular equations. You can't see this t variable and how it's acting on the graph. So we kind of give an indication by drawing these arrows. All right, and those arrows we call the orientation of the graph. Or rather they give the orientation of the graph. So like I mentioned, that one swoopy looking curve that we had um, on Desmos, I said that that could be like the flight of a bird or something. And so this is usually actually why we use the variable t as the parameter, because a lot of times it stands for time and how something is changing over time. And so it's actually important to know the orientation of the curve, like where it starts and where it goes as t increases, small to big. So now I want to go back over to Desmos and show you something else, because it turns out that there is a curve that you already know how to parameterize. You just don't know that you know it. All right, so the one that you know is this guy. I'm going to zoom in on him. Okay, and if I show you the equation of this, the rectangular equation, you're not going to be surprised because you know everything about conic sections from section 9.1. All right, so that's x squared plus y squared is equal to 1. So it's just a circle centered at the origin with a radius of 1. All right, and like I said, you actually know the parameterization for this without even knowing that you know it. And I'm going to reveal this to you with the folder that's labeled brace yourself. So you may want to make sure you're sitting down and take a deep breath. So here it comes. Okay, so yeah, you recognize this circle, right? So this one comes from trigonometry, the unit circle that tells us the sine and cosine of a few angles. Okay, so let's get rid of all that clutter. Let's think of it this way. This is a little bit easier to look at. Okay, so this is what the unit circle does in your trigonometry class. For any angle theta, The coordinates there give you the cosine of the angle, comma, the sine of the angle, and it doesn't matter which angle I pick, okay? Your x coordinate gives you the cosine of that angle, and the y coordinate gives you the sine of the angle. All right, so that was the whole point of that unit circle that you had to learn about in your trigonometry past. All right, so it turns out that this also actually completely defines the circle. So if I turn off the rectangular equation, and I'm going to come here, I'm going to type this in as a parametric equation. Now remember, we usually use t for the variable, so I'm going to say cosine of t, grab my cosine function and get my t. And right now, Desmos doesn't realize I'm doing parametric equations yet, but it will in just a second. So I'm going to do cosine t, comma, sine t. And once I put those two there, it goes, oh yeah, you're doing parametric equations. And then I'm going to tell it that t, which is my angle theta, t is taking the place of theta, I want that to go from 0 to 2 pi to trace the whole circle. So I'm going to say 0 to 2 pi. And there it gives me the exact same equation, the exact same graph as x squared plus y squared equals to 1. And that kind of makes sense because we know that cosine squared plus sine squared is equal to 1. All right. So this is the parameterization of the unit circle. X is equal to cosine t and y is equal to sine t. All right. So when we get back together in class, we'll talk a little bit more about the things that we can do with parametric equations. See you then.